All right, so we're going to look now at the rest of 16.7 and 16.8, which is really short. And that will kind of get us through all of our acid-base chemistry. And then what we'll do is we'll look at salts on Wednesday, begin that process, and do a lab on Thursday. Okay, so this table here is just kind of summarize everything we just did. If you can do this, then you've basically picked up on all the concepts. We're going to have to use a little bit of our equations, a little bit of Rice tables to kind of work through all of this. So we're going to take a reaction. This is, and I'm going to start showing this. This is sodium hypochlorite, and it's going to go into a salt. Oh, sorry. But the equation we're interested in is actually this. This is our base. So I'm going to put this down here. We have OCl minus plus water. Remember with bases, we tend to do that, right? Is HOCl plus OH minus. Okay. So this is what we're interested in because this is just making that. That's a NAP, right? Sodium. So I don't really care about that, but then when this hits the water, I get this. So first we get here, and then we're here. All right. Now, if I just want the POH, that's pretty easy because I'm going to dump all this sodium hypochlorite into the beaker, and all of a sudden it generates this pH. You'd think that this would be neutral to salt, but it isn't, because it dumps this base in there with it, right? That's the anion. This is going to act as a base. So this is going to put the pH up above neutrality. So if I want to find POH, I'm just going to take 14 minus 9.5, and that equals 4.50. If I want to find the hydrogen ion, the hydroxide concentration, then I'm going to take 10 to the minus 4.50, and that's going to be 3.2 times 10 to the minus 5 molar. Okay. Now, if this is 3.2 times 10 to the minus 5, so if this is here, then this has to be the same, doesn't it? Because when I make this, I make equal amounts of this and this. So this one is also 3.2 times 10 to the minus 5 molar. This is the one we don't know. So it's just like the problem we did before. So I'm going to go ahead and do my Rice tables. Now, I don't know what this is, but I have KB, so this is a slightly different twist. If you notice, I've not been given a molarity of an initial concentration of this. So what I'm going to do is I'm going to call this Y. And then I have some Y amount, right? And 0 and 0. I don't know what that is. All right, change. So this is R, this is I, and this is C. Now, this is going to be minus X. This is going to be plus X and plus X. All right? So then I'm going to do my equilibrium, and I'm going to get Y minus X, X, and X. Now, I know what X is, don't I? Because I have done that up here. Each of these concentrations is 3.2 times 10 to the minus 5. This is 3.2 times 10 to the minus 5. And this is Y minus 3.2 times 10 to the minus 5. Okay? I've designated this as Y. You could call it whatever you want, but I'm doing everything's the same, only I don't have a number here. I have to find that number. But I do have a KB, so I'm going to dump all of this into KB. So KB is going to be equal to 3.2 times 10 to the minus 5 squared, right? This times this divided by Y minus 3.2 times 10 to the minus 6. Or what did I do? Times 10 to the minus 5. Oops, sorry. Okay. I go through and I solve for y, and so KB is equal to what? 3.3 times 10 to the minus 7. So all of this is equal, this should be a 5, yeah. All of this is equal to KB, and it turns out that y is equal to 3.1 times 10 to the minus 3 molar. Now, this is all in 1 liter, so I'm good. So this goes here. 3.1 times 10 to the minus 3 molar was the initial concentration of that. Okay. Real quick, a little bit about KB and Ka. Oftentimes, when you look up Ka and Kb values, you're only going to find Ka, right? So in your textbook, in your appendix section, here are some of your common Kas. I think you can also pull a drop down in your OWL and it'll give you some of your Kas. Kbs are a lot less. In fact, a lot of tables, there are no Kbs. But you can get to Kb through Ka. So that's what we're going to show you how to do, because you might need to do that. In fact, it's really common in FRQs where they'll have a base reaction, but they'll give you a Ka, and you've got to get the Kb in order to continue. All right, so these are my 2 reactions. This is dissociation of my acid. This is the reaction of the conjugate base with water, right off your formula chart. This is Ka, this is Kb. And so if I rewrite these right off my formula chart, then I get this times hydroxide divided by concentration of A minus. Now, again, I know these values. If I add these reactions together, I don't have the K question mark, this K, but I can remember if we have the 2 and it makes my target reaction, I can multiply these together and get my value. So if you notice, if I do this, I get water, liquid, is in equilibrium, which H plus and OH minus. So that is my target reaction, which is really the autoionization of water when I have these 2. So what that means is that Ka times Kb is equal to the concentration of H plus times the concentration of OH minus, because if I add these, I multiply these. But look at what that is. That's my reaction. Well, what is that? That is Kw. So Ka times Kb is equal to Kw, right? So we're going to put that here. If I take the logs of everything, I can also say my pKa plus my pKb is equal to can't write today, pKw, which is equal to 14. Okay? So now there's this relationship between Kb, Ka through Kw that will allow me to do some calculations. So, for instance, this is acetic acid. That's its Ka. Its pKa, remember, is just the negative log of 1.8 times 10 to the minus 5, which is equal to 4.74. And I do the same here, and I get 7.54. Now, remember that this is the stronger acid. It has the larger Ka, lower pKa. That's going to be tricky. The lower the pKa, the stronger the acid. It follows right with pH. The stronger the acid, the lower the pH. All right, now, I can do the same with pKb. This is the acetate ion, right? And the acetate ion, the hypochlorite ion, how are we going to figure out what the values of these are? What I can do if I only have Ka and I want Kb, if Ka times Kb is equal to 1.0 times 10 to the minus 14, if I want Kb in this case, I'm going to divide both sides by Ka. Therefore, Kb is equal to 1.0 times 10 to the minus 14 divided by, in the case of acetate, what is my Ka? My Ka is what we calculate, is what we have over here. So I'm going to look over here. That is the Ka of acetic acid. So I'm basically going to put that here. 1.8, what was it again? 1.8 times 10 to the minus 5. So I plug that in, and I get 5.6 times 10 to the minus 10. So what this allows me to do, if I know the Ka of the conjugate acid of this base, which would be this, and I was given the Ka, I can get to Kb by doing this simple calculation, right? Same with this one. I may not know the Kb of this, but what if I know the Ka of this? I can then calculate the Kb by plugging that into here, and if I do that, I get 3.3 times 10 to the minus 7. So what you're going to have to start doing is you're going to have to start being really careful about whether you're given Ka or Kb. Make sure you look at your subscripts so that you know for sure what you're given. But either way, you can get to either of them through the other using the KW.